After studying this module, you shall be able to know how the statistical thermodynamic approach is utilized for calculating equilibrium constant in transition state theory, derive the relationship between rate constant and partition function, and appreciate the two different approaches to transition state theory. We have already discussed in detail the relationship between rate constant and temperature given by Arrhenius equation. We also studied collision theory and the classical thermodynamic approach to transition state theory as well. We did derive the expression for rate constant as per classical thermodynamic approach to transition state theory, where K is equal to RT upon H NA C naught into e to the power minus delta H naught upon RT into e to the power delta S naught upon R. Now, in this module, we will discuss in detail the statistical thermodynamic approach to transition state theory. Now, before coming to the statistical thermodynamic approach, let us quickly review what is transition state theory and its major assumptions. The transition state theory depicts the formation of transition state complex that is obtained from the reactants A and B as a preceding step for the formation of products. This theory is essentially applicable to gaseous reactions, and it is assumed that the transition state complex is in equilibrium with the reactants and that the rate at which transition state complex decomposes to products depends on the rate at which it passes through the transition state. The major assumptions of this theory are: collisions are responsible for a chemical reaction, and equilibrium exists between reactants and the transition state complex, and the reaction coordinate describing the conversion of transition state complex to product can be mapped onto a single degree of freedom of transition state complex. If product formation involves breaking of a bond, then vibrational degree of freedom corresponding to bond stretching is taken as reaction coordinate. For the reaction A plus B giving transition state complex giving products, the equilibrium constant is of the form the concentration of transition state complex upon concentration of the reactants A and B. And the rate constant as per transition state theory depends on two factors. Firstly, the concentration of transition state complex, and secondly, the frequency of decomposition of transition state complex, which we expressed as R is equal to frequency into concentration of transition state complex. This expression for rate further simplifies to the form R equals to frequency into equilibrium constant into concentration of A into concentration of B. Now, statistical thermodynamic approach comes into picture as the concentration of the transition state complex is calculated from partition function of the reacting species, and this partition function is a statistical thermodynamical concept. Before proceeding, let us know what is a partition function and why it is so significant. Partition function is one of the most important properties for any system in statistical mechanics. It contains all the information about the system and is therefore referred to as storehouse of information. This partition function depends on temperature and is a number only and is therefore unitless. Now, let us consider an elementary reaction A plus B giving products, for which the rate is equal to rate constant into concentration of A into concentration of B. Now, let us consider the same reaction taking place via transition state complex, that is A plus B giving transition state complex giving products. And as per the assumptions of transition state theory, we know that rate is equals to rate constant into concentration of the transition state complex. Now, equating the rate expression that we have obtained considering the transition state equation for the reaction and that obtained by considering the elementary reaction, we get K into concentration A into concentration B equals to K into concentration of transition state complex. Now using this, we get the expression for rate constant as K into concentration of the transition state complex upon concentration of A into concentration of B. Now since there exists an equilibrium in the reaction A plus B giving transition state complex, the equilibrium constant for the reaction is expressed in the form capital K upon C naught, which becomes equals to concentration of transition state complex upon concentration of A into concentration of B. C naught over here is the unit concentration which is employed to make the equilibrium constant term dimensionless. Now with this, the rate constant expression becomes K as obtained from transition state theory into equilibrium constant upon C naught. Now if one can derive expressions for the rate constant obtained from the transition state equation and the equilibrium constant, one can calculate the rate constant for the reaction, and it is this equilibrium constant capital K which can be expressed in terms of partition function. The statistical thermodynamic interpretation on equilibrium constant in terms of partition function has been taken up in detail in our previous module, and over here we will be utilizing the same to obtain the rate constant in terms of partition function. So now let us consider a gaseous reaction of the form A of A plus B of B giving C of C plus D of D. The equilibrium constant for the reaction becomes P subscript C upon P naught whole to the power C, P subscript D upon P naught whole to the power D upon P subscript A upon P naught whole to the power A into P subscript B upon P naught whole to the power B, where PC, PD, PA and PB are the partial pressures in terms of molar concentrations, that is Pi is equals to RT into concentration of the component X, and P naught over here is taken as 1 bar again to make the equilibrium constant dimensionless. Now using the thermodynamical relations between delta G and equilibrium constant, we have delta G equals to minus RT ln Kp, and also we know that G is equals to H minus Ts, which using first law becomes E plus Pv minus Ts, and also from statistical thermodynamics we know the relation between entropy and partition function as S equals to Kb ln capital Q plus E upon T. Over here Q is the macroscopic partition function for the whole bulk system, and since we have considered gaseous reactions, which means we have considered non-localized indistinguishable particles interacting with each other. For such a system, partition function, or rather macroscopic partition function, takes the form capital Q equals to small q to the power n upon n factorial, where n refers to the total number of particles in the system and small q refers to the partition function with respect to particle. Now using this, the expression for entropy becomes Kb logarithm q to the power n upon n factorial plus E by T, and delta G becomes minus RT logarithm q by Na. Now using these thermodynamic relations between entropy and partition function, Gibbs free energy and partition function, Gibbs free energy and equilibrium constant, we get the value or the expression for equilibrium constant as Kp is equals to Qc to the power C, Qd to the power D upon Qa to the power A into Qb to the power B into 1 upon Na whole to the power C plus D minus A plus B. Over here Na refers to the Avogadro's number. Now we need to pay attention to the form of partition function that we have in this equation. As per transition state theory, we have already assumed that a vibration of the transition state complex tips it through the transition state, or one can say one vibrational mode is responsible for product formation. This implies that the partition function so expressed in the equilibrium constant equation is the vibrational partition function, and so the equation can be rewritten in the form Kp is equals to QCV to the power C into QdV to the power D upon QAV to the power A into QBV to the power B into 1 upon Na whole to the power C plus D minus A plus B. Over here the subscript V refers to that of vibrational partition function. Before proceeding further, we need to know the form of vibrational partition function. We have already discussed in detail vibrational partition function in our earlier modules, and over here we will be using those results. Let us briefly review the form of vibrational partition function. Vibrational partition function for a diatomic molecule. This can take up two forms. Firstly, with 0 point energy, where the energy expression is equals to V plus 1 upon 2 into H into frequency, where V is the vibrational quantum number, and this is the expression that we have with 0 point energy, which means that even for quantum number 0, the energy value will not be 0. For this, the partition function that we obtain is of the form Qv equals to e to the power minus h into frequency upon 2 into Kb into T upon 1 minus e to the power minus h into frequency upon Kb into T. Over here the frequency refers to the frequency of vibration corresponding to the transition state complex. Kb is the Boltzmann constant and h into frequency by 2 is the 0 point energy. For 1 mole of the reactants giving products, Na into h into frequency upon 2 Na Kbt becomes Na into h into frequency upon 2 RT, as Na into Kb gives R, that is the gas constant. With this, the vibrational partition function expression becomes e to the power minus Na h into frequency upon 2 RT divided by 1 minus e to the power minus Na into h into frequency upon RT. And using this vibrational partition function, the equilibrium constant expression becomes QCV to the power C into QDV to the power D upon QAV to the power A into QBV to the power B into 1 upon Na to the power C plus D minus A plus B. Now, the other case can be where vibrational energy is expressed as Planck's constant into frequency. Now, this is the energy expression which is without 0 point energy. The other expression for energy can be EV equals to V into H into frequency, where capital V is the vibrational quantum number and this energy expression is without 0 point energy, which means that for quantum number equal to 0, the energy becomes 0. Now, for such a system, the vibrational partition function is obtained as Qv dash equals to 1 upon 1 minus e to the power minus h into frequency upon Kbt, where frequency over here corresponds to the frequency of vibration. Kb, as similar to the previous case, is the Boltzmann constant, and for 1 mole of the reactants giving products, the expression modifies to Qv dash equals to 1 upon 1 minus e to the power Na into h into frequency upon RT. With this, the equilibrium constant expression becomes Kp equals to QCV dash whole to the power C into QdV dash whole to the power D upon QAV dash whole to the power A into QBV dash whole to the power B into 1 upon Na whole to the power C plus D minus A plus B. Or one can even write the equilibrium constant expression Kp as QCV dash whole to the power C into QdV dash whole to the power D upon QAV dash whole to the power A into QBV dash whole to the power B into 1 upon Na to the power C plus D minus A plus B into e to the power minus delta E naught upon RT. Over here, delta E naught is the 0 point energy which is obtained as C of ECV naught plus d of E dV naught minus A of EAV plus B into EBV naught. Now considering the reaction A plus B giving transition state complex, we get the expression for equilibrium constant as Qxv dash upon QAV dash into QBV dash into 1 upon Na whole to the power minus 1 into e to the power minus delta E naught upon RT. Specifically, partition function for the transition state complex becomes Qxv dash equals to Qxv star into 1 upon 1 minus e to the power minus NaH into frequency divided by RT, where Qxv star is the vibrational partition function corresponding to that one vibrational mode that is responsible for bond breaking and product formation. Now using this in the equilibrium constant expression as Qxv star into 1 upon 1 minus e to the power minus NaH frequency upon RT divided by QAV dash into QBV dash whole into 1 upon Na to the power minus 1 into e to the power minus delta E naught upon RT. This expression can be simplified in the form equilibrium constant equals to K star into Na into 1 upon 1 minus e to the power minus NaH into frequency upon RT. Over here K star refers to Qxv star upon QAV dash into QBV dash into e to the power minus delta E naught by RT. Now expanding the exponential term in the equilibrium constant expression, e to the power minus NaH into frequency upon RT gives us 1 minus Na into h into frequency upon RT plus higher terms. Now ignoring the higher terms and substituting this back in the equilibrium constant expression gives us equilibrium constant equals to K star into Na into 1 upon 1 minus 1 plus Na into h into frequency upon RT. This further simplifies to equilibrium constant equals to K star into Na into kBt by h into frequency, where frequency is the term responsible for breakage of bond. For the reaction A plus B giving transition state complex, we expressed the rate as frequency into capital K, that is the equilibrium constant, into concentration of A into concentration of B. Now substituting the value of equilibrium constant gives us the rate as well as the rate constant for the reaction. So we get rate constant as frequency into K star into Na into kBt upon h into frequency, which simplifies to K equals to K star into Na into kBt by h. Now substituting the value of K star in the expression for rate constant, we get rate constant K as Qxv star upon QAV dash into QBV dash whole into e to the power minus delta E naught by RT into Na into kBt by h. Now one can see that this equation relates the rate constant to partition function. This implies that the value of rate constant is dependent on the factor Qxv star upon QAV dash into QBV dash, and the other factors are more or less constant. Now let us see how different values of partition function results in different values of rate constant. Let us assume the reaction between A and B, that is the gaseous atoms A and B, giving a transition state complex which is diatomic, which leads to ultimately product formation. Now since we have considered two atoms A and B, QA and QB correspond to translational partition functions respectively. Now translational partition function has the form QA equals to 2 pi ma kBt upon h square whole to the power 3 by 2 into V. Over here we refer to this as QAT dash, and QB has the form 2 pi mb kBt upon h square whole to the power 3 by 2 into V, which is again over here used in the form QBT dash. Now since the transition state complex is a linear diatomic molecule with 3 translational degrees of freedom, 2 rotational degrees of freedom and 1 vibrational degree of freedom, the partition function for the transition state complex is expressed as Qx star equals to Qt cube into Qr square into Qv. Over here Qt refers to translational partition function, Qr to rotational partition function, and Qv vibrational partition function. And we also know that we considered one vibrational degree of freedom has already been taken into account as we considered one vibrational mode responsible for product formation. So the partition function for the system or the transition state complex thus becomes Qt cube into Qr square. Similarly, if we have Na atoms in a system, there will be 3 Na degrees of freedom. If the molecule is linear, there will be 3 translational, 2 vibrational and 3 Na minus 5 vibrational degrees of freedom associated with that system. And if the molecule is non-linear, then there will be 3 translational, 2 rotational and 3 Na minus 6 vibrational degrees of freedom. So, for the transition state complex, we have Qt cube, that is Qx star T cube, as 2 pi Ma plus Mb kBt upon h square whole to the power 3 by 2 into V, and Qr takes the form 8 pi square I kBt upon sigma h square, where I is the moment of inertia, which is expressed as product of reduced mass, where R is the internuclear distance taken as dA plus dV upon 2, and mu refers to the reduced mass, which is taken as 1 upon Ma plus 1 upon Mb, and sigma is the symmetry number, which is taken as 1 for heteronuclear molecule. So for atom A, there will be 3 translational degrees of freedom and the partition function becomes Qt cube. Similarly, for atom B, it becomes Qt cube, whereas for the transition state complex, it becomes Qt cube into Qr square. So the rate constant for the reaction A plus B giving transition state complex in terms of partition function can be expressed as K equals to Qt cube into Qr square upon Qt cube into Qt cube into constant. So this further reduces to Qr square upon Qt cube into constant. One needs to know that the translational degree of freedom or the partition function Qt, they have a magnitude of energy associated with them, which is of the factor 10 to the power 30. Whereas for rotational degree of freedom, this energy factor becomes in the range 10 to 100, and for vibrational degree of freedom, it becomes 1 to 10. Now, the way we derived the expression for rate constant for a diatomic transition state complex, we can even derive the expression for rate constant based on partition function values for different reacting systems. For example, if we have 2 reactants A and B, and if we consider the possible combinations, if both are atoms, then the expression for K becomes Qr square upon Qt cube. Now, if the reactant A is diatomic and reactant B is also diatomic, the expression becomes Qv4 upon Qt cube into Qr square for a linear molecule, whereas if the molecule is non-linear, then the expression becomes Qv cube upon Qt cube into Qr1. One can note that except for atoms, all other systems have vibrational partition function present in the numerator and translational and rotational partition function in denominator. It is important to note that these aspects of particle behavior and its relation with rate constant comes from the statistical thermodynamic approach. Let us now look at the limitations of the statistical approach. Over here, we need to know the geometry of transition state. We need to know the height of barrier and 0-point energies of reactants and the transition state. And we also need to know the vibrational spectrum of the transition state. Also, the calculations done for the determination of rate constant is mainly useful for gas phase reactions, since the partition function for gaseous phase can be easily determined. But if we talk about condensed phase reactions, then partition function is difficult to determine. So instead of statistical parameters like partition function, thermodynamic parameters are preferred. So in all, in this module we studied the statistical thermodynamic approach to transition state theory. Over here we derived the expression for rate constant in terms of partition function. We considered a reaction between two atoms A and B giving transition state complex which we assumed to be diatomic, which ultimately gives products. For this reaction we obtained the expression for rate constant as Qx V star upon Qa V dash into Qb V dash into e to the power minus delta E naught upon RT into Na into Kbt by H, where we further assumed that one vibrational degree of freedom is responsible for breaking of bond or product formation. Now this equation that we obtained for rate constant in terms of partition function implies that the value is dependent on the factor Qx V star upon Qa V dash into Qb V dash, while other factors are more or less constant. With this, we will take up solution kinetics in the subsequent modules.